If you consider the methods we've discussed thus far, they fall into two categories. We either capture a single snapshot of a three-dimensional scene, or we take a sequence of images, but assuming that the scene is stationary. That is, we have assumed thus far that objects in the scene do not move. But we know that most things in the real world are in motion most of the time. And we are interested in measuring the motion of objects in the scene. And that is the problem of computing optical flow. So we're going to develop a method for estimating the motion of scene points in the image from a sequence of images taken in quick succession. So first, we're going to talk about the notion of motion field. When you have a point moving in the three-dimensional scene, its projection onto the image via perspective projection is what's referred to the motion field. But we can't directly measure the motion field because in images, all we have are brightness patterns. And what we can do is measure the motion of brightness patterns. The motion of brightness patterns in the image is referred to as optical flow. We look at when optical flow corresponds to motion field and when it does not. Then we're going to set about measuring optical flow. It turns out that we can't directly measure optical flow uniquely at each pixel by simply looking at the brightness variations of that pixel. But what we can do is to come up with what's called an optical flow constraint equation. It constrains the optical flow at a pixel. In order to constrain the problem and solve for the optical flow at each pixel, we use a neighborhood of pixels. And that brings us to the technique called the Lucas-Canade method for estimating optical flow. We'll see how that method works and the results that it produces. Then we'll talk about the problem of large motion. Let's say you have an object right here, and then it suddenly moves to a very different position. The motion is substantial enough that we can't directly use the optical flow constraint equation because the optical flow constraint equation is based on local derivatives of the image. So we come up with this representation of a pair of images, which is called the resolution pyramid. We use the pyramid to go down to lower resolutions to compute optical flow using the optical flow constraint equation, and then propagate that information to higher resolutions to ultimately compute the optical flow at all pixels in the image, despite the fact that they may be very large motions. And finally, we're going to talk about a few interesting applications of optical flow.